अस्सलाम वालेकुम क्लास, कैसे हैं आप लोग? खैरियत से हैं? ठीक ठाक हैं? उम्मीद है आप लोग ठीक होंगे। अल्हम्दुलिल्लाह, I'm fine. In today's video lecture, we will talk about the microwave antennas. Uh, Microwave antennas are to understand microwave antenna. First, we have to define the microwave frequency. Microwaves are nothing but electromagnetic waves with wavelengths at micro levels, and microwave antennas are small in size. As you all remember that in very first lecture we have discussed the frequency spectrum of the and frequency spectrum in which we have described the microwave range, and as from this spectrum it is known that the microwave are the waves which have the wavelength at micro level, very small wavelengths. And as we know that from the relation that lambda is equal to c by f, that means uh, length and the frequency are inversely proportional. That means the higher the frequency, the minimum is the size of the antenna. So it simplifies that where the frequency is higher, the size of the antenna will be small. Okay. From the introduction, the size of the antenna depends only on the frequency that it has been described right now. The frequency, as higher the frequency is, the lower the size of the antenna, and vice versa. It is very difficult to define that the micro antennas are typical for their range, as we know that there are some antennas which can work on both of the spectrum, that is, both of the ranges, or in dual range. There are many antennas exist that can work on dual frequencies. Microwave antennas have there are various microwave antennas exist, but the popular ones are reflector antennas, horn antennas, dielectric and metal lens antennas, slot antennas, and microstrip antennas. As we know from the spectrum that the microwave is from 1 giga to 100 giga is the microwave frequency range, and the benefit of working on the higher frequencies is that we can basically achieve the narrow beamwidth in both vertical and horizontal planes. Okay, uh, we will more focus on reflector antennas for microwave in today's lecture, and the horn antennas. The type of reflectors we have: rod reflectors, cone reflectors, horn reflectors, parabolic reflectors, plane reflectors, cylindrical reflectors, and spherical reflectors. We are much more interested in horn reflectors and parabolic reflectors, so we will focus on these two types only as per our course outline. Okay, first we talk about the parabolic reflectors. Parabolic reflectors are the reflector with the shape of the paraboloid and employs the properties of parabola. Parabolas have the parabolic shape. It can also define a reflector with a part of paraboloid revolution. Basically, the parabolic reflector works as given in the geometry, that there is a focal point of the parabolic reflectors on which our feed antenna is being connected, and as per the transmission geometry given, the signals are more focused on the focal point. From the focal point, the antenna feed from the at the focal point, the antenna feed antenna has been installed. This feed antenna can transmit the signal, as shown that the signal is being directed to the parabolic reflector, and that reflector basically reflects the component of the signal into the atmosphere. This is the radiation pattern of the parabolic dish of the parabolic antenna. Below given is the geometry that A and B is the axis of the parabola, C and D is the mouth diameter of the antenna, A and F is the focal length, A is the vertex, F is the focus, C A D is the parabola, CD is also known as directrix, and the ratio of AF over CD is the aperture of the parabola. As given in the as given in the diagram, the receiving geometry, is given in the block diagram that as the signal reaches the parabolic reflector, the parabolic reflector reflects the component of the received signal to the focal point at which our antenna or the primary antenna is installed, which receives the signal and given to the device for decoding or for the display purpose. As it is defined, the operation of parabolic reflectors, the parabolic reflector is only concerned about the focus of the signal in both, that is in transmission and reception. The half power beamwidth is given as 70 lambda by d, and beamwidth from first null is 140 lambda by d, that is 205. It is noted that the reflector has the only operation which transfers the spherical wave into plane wave. The reflector of the only reason to put on is to convert the spherical wave into the plane wave. It is given that the main purpose of the reflector is to convert a spherical wave into a plane wave. It is given in the diagram that the spherical waves convert into the plane wave. The directivity of the parabolic antenna is given as d is equals to 9.87 multiplied by dA over lambda whole square. If the aperture is rectangular and uniform and large, if the aperture is uniform and large and rectangular, the half power beamwidth can be calculated as 57.5 lambda over L, and beamwidth from first null will be 115 lambda over L. The directivity is also changed for the rectangular large aperture, and it would become 4 pi a over lambda square. The power gain of the parabolic reflector antenna is 4 pi over lambda square AC, where AC is the actual area and for specifically it will be 6.4 multiplied by d over lambda whole square. The salient features of the parabolite reflectors are it has a very sharp directional beam and several side loops. The shape is like the fat cigar. The primary antenna that installed at the antenna that installed at the focal point is known as the primary antenna. And if the primary antenna is non-directional, the beam width and half power beam width formulas would be like this, would be like the given formulas. The gain of the antenna parabolic reflector is influenced by aperture ratio. Definitely, as large as the aperture ratio, the maximum is the efficiency of the gain of the antenna. Directivity with respect to isotropic antenna is D equals to this. Effective radiated power is equals to is the product of input to the power gain. We can obtain very large gains and narrow beamwidth by using the parabolic reflectors. Parabolic reflectors does not work at low frequencies. For the maximum efficiency, the diameter of the parabolic reflector should be equal to or greater than 10 lambda. Primary antenna radiation characteristics are the reason which uh, which increase or decrease the efficiency of parabolic reflectors. They have several applications in communication and radar. The reflector is called the secondary antenna and the feed antenna which is installed at the focal point is called primary antenna. They also have some disadvantages of the parabolic reflectors. The radiation beam is a pencil beam and is surrounded by side loops. These side loops create electromagnetic induction, and the effect of electromagnetic interference is more prominent in low noise receivers. Diffraction is the other problem of the parabolic reflectors. The primary antenna does not radiate evenly at the reflector and distortion is introduced. In order to avoid the flattered beam, we can also use horn feed antenna. There are several types of parabolic reflectors, such as cut or truncated parabolic cylinder, pillbox and cheese antenna, offset parabolic reflector, torus antenna. The main advantage of the parabolic reflector is the sharp beam width. Now, as per the course outline, we have to concentrate on the another primary antenna that has been used in the parabolic reflector is the horn antenna. Horn antenna is basically the shape of the horn. It is a radiating element which has the shape of the horn. It is actually a waveguide which is open at the one end or feed at the one end and flare out the signal at the other end. Several types of horn antennas are defined: sectorial horn, pyramidal horn, conical horn. Sectorial horn have other two types. One is the H-plane horn and the other is the E-plane horn. As shown in the figure, this type of shape introduces H-plane horn, which is flat type horn. This type of shape as E-plane horn, as it is somehow been not flat as compared to the previous picture. And this shape is known as the pyramidal horn, which is flat but has have some specific height. And this cone type horn is known as the conical horn. As the sectorial horn, H type and E type, H plane horn uh, have the radiation parallel to the magnetic field, and E plane horn has the radiation parallel to the electric field of the signal. This is the geometry given. This lambda is known as the path difference. This L is the axial length. D is the aperture dimension, and theta is the this theta is, or this theta is the same, that is known as flare angle. Okay. Operation of the horn. The electromagnetic wave propagation in a waveguide is different from that of the free wave. Definitely, the radiation is restricted by the walls of the waveguide. After reaching the mouth, waves spread literally, and wavefront becomes spherical. At the mouth of the waveguide, there exists near field region where the wavefront is complicated. This is considered to be a transition region where change of propagation from waveguide to free space takes place. Definitely, as the signal reaches there, it is the transition from waveguide to the atmosphere. As the waveguide, as the waveguide impedance and free space impedance do not match, all of the waveguide are flared out. This flared out structure is called the horn. The design equation of the horn antenna is given as theta is equal to tangent inverse d over 2L. After simplified, becomes L is equal to d square over g sigma. This is the half power beamwidth of the optimum flared horns. This is lambda over dE for E type and 6.7 lambda over dH for H type. These are the directivity equations: 7.5 A over lambda square and power gain 4.5 over A over lambda square. There are certain applications exist for the horn antenna. They can use at microwave frequencies where moderate gains are sufficient. They can also use as feed elements for parabolic reflectors and other reflectors. They are often used in laboratory for the measurement of different antenna parameters. Salient features can be horn becomes small if the flare angle is small. Its radiation pattern is directive. Wavefront is spherical, mouth area is small and directivity is small. Flare angle is related to axial length. At these configurations, the directivity is 120. Directivity of pyramidal horn is more as compared to other horn antennas. It is used as radiator. can be used with the waveguides. It is used as primary antenna for paraboloid. I've been told you a moment before that they can be used as the feeding antenna for the paraboloid or parabolic reflector. The gain of the conical antenna is optimal for given slant length of flare L, which is given as 3 over lambda. The directivity of a lossless horn antenna is its gain and is given by 4 pi n over lambda square, where A is the actual area, N is the aperture efficiency, lambda is the wavelength. In case of rectangular horn, actual area is equals to d into dh. D is the aperture size of in E plane and dh is the aperture size in H plane. In case of conical horn, AE pi d is the aperture diameter, and its efficiency is if aperture efficiency is zero point 0.6, the directivity can be 7.5 AA or lambda square. This is about the conical horn antenna. That is the overview of the microwave antennas. I will further define the discuss the problems related to the reflectors and the horn antenna. So that is all for the microwave antenna theory. Inshallah, we'll discuss the question related to the microwave antenna later. Thank you very much.